spending most of your time doing research. As you can see here, we have two water activity meters.
Water activity? I remember learning about that. That's the thing that tells you the amount of water in food, right?
Actually, not quite. So moisture content tells you how much water is in food. But water activity says something a little bit different.
Okay, so if these instruments can't tell us the amount of water in food, then what's the point?
Actually, water activity is really important in predicting the stability of different food products. So we can use water activity to predict the shelf life and types of reactions that will occur in food over time.
Cool.
So let's do a little refresher about moisture content versus water activity. So let's get started. What do we mean by moisture content and water activity? Let's define these two terms first. Moisture content is the amount of water contained in the material. It is commonly reported on either a wet basis or dry basis, which we calculate as follows. Wet basis moisture content is equal to the mass of water in the sample divided by the total mass of the sample. Dry basis moisture content is equal to the mass of water in the sample divided by the mass of solids in the sample. So what's water activity then? Water activity, or AW, is defined as the ratio of the partial vapor pressure of water above a food to the vapor pressure of pure water at the same temperature and pressure. Let's first talk about the vapor pressure of pure water. When water is placed in a closed container, water molecules with enough energy will escape into the headspace in the form of water vapor. Those vapor molecules are in constant random motion and exert a pressure on the top and sides of the container. The more water molecules that exist in the headspace and the faster those molecules are moving, the higher the vapor pressure. The vapor molecules are in a dynamic equilibrium with the liquid water. There are constantly vapor molecules returning to the liquid state and liquid water molecules escaping to the gas phase, but the overall pressure in the container stays constant while this exchange occurs. Vapor pressure of the food is the same basic concept. In a closed container, water molecules in the food can escape in the form of water vapor and enter the headspace of the container, exerting a pressure on the top and sides known as the vapor pressure. Some of the water molecules in the food cannot escape into the headspace because they interact with components of the food. The vapor pressure of the food, divided by the vapor pressure of pure water, is equal to the water activity. So moisture content and water activity aren't the same, but they at least relate to each other. Foods with higher moisture contents tend to have high water activities, but it's usually not a linear relationship. If we plot moisture content versus water activity, we can visualize this relationship. We call this type of graph an isotherm, which we often divide into three regions that show different water mobility and food properties. In region 1, moisture content and water activity are both low. Water molecules are tightly held by the food and have limited mobility. In region 2, moisture content is still relatively low, but water activity increases rapidly with small increases in moisture. Water molecules interact with the food, but have some mobility. In region 3, both moisture content and water activity are high, and water molecules have high mobility. In addition to different moisture contents, foods in each of these regions have different textural properties. Foods in region 1 tend to have a dry or crisp texture. Foods in region 2 tend to have a chewy or moist texture. And foods in region 3 tend to have a soft or juicy texture. Food stability also differs between water activity regions. We can gain insight into differences in food stability by using the isotherm as a template for a map of sorts. Many reactions in microorganisms that affect the quality and stability of foods have water activity dependent reaction rates. So, by plotting the reaction rates, or growth rates for microorganisms, against the water activity, we can predict which factors will affect a food's stability based on the food's water activity. The number of factors that can reduce food stability increase with AW. We can see that in Region 1, lipid oxidation is the main stability concern, and most other factors like microbial growth, non-enzymatic browning, and enzyme activity are not problematic. In Region 2, lipid oxidation, non-enzymatic browning, and enzyme activity can occur to some extent, but microbial growth is still not a big concern. However, in Region 3, foods are susceptible to all factors discussed, including lipid oxidation, non-enzymatic browning, enzyme activity, and microbial growth. Consequently, foods in Region 1 have high stability, or long shelf lives, foods in Region 2 have intermediate stability, or intermediate shelf lives, and fresh foods in Region 3 have low stability, or short shelf lives. However, foods in Region 3 can undergo processes like canning and pasteurization that improve their stability and thus give them longer shelf lives. Some examples of food products in Region 1 are cereal, chips, and crackers. Foods in Region 2 include chewy granola bars, raisins, and fruit roll-ups. Food examples for Region 3 include fresh fruits and vegetables, milk, and meats. So, to summarize, moisture content is the amount of water in a food, while water activity is the ratio of the partial vapor pressure of water in a food to vapor pressure of pure water at the same temperature and pressure. We can relate the concepts of water activity and moisture content using a graph called an isotherm, which we divide into 3 different regions. Foods in each of these water activity regions have different moisture contents, textural attributes, and shelf lives. So while moisture content and water activity both relate to water in foods, they have different definitions and implications. And that's what's up with water activity.